welcome again to the Academy. This is part of a video series on Cal 3 topics, and this episode we'll be talking about line integrals, which are also called path integrals. So before we've been talking about derivatives of functions of multiple variables. Now I want to talk about a little bit how to take integrals. Now integrals in a single variable calculus are pretty basic. It's just, you can think about a definite integral as the area under a curve of f of x dx from a to b probably. And now this concept can be extended to functions of more than one variable. For example, well, let's just visualize this. This interval right here is all you can integrate if you have just one variable. But let's say you have a function that looks something like this, f of x, y. Now, instead of just integrating over an interval, because you have the whole xy plane, you can integrate over a path. Something like this. And you can imagine that this is the area of this function under this function over this particular path. So something like this. Imagine sort of like a curvy wall coming down here. You can visualize that. Basically, this is the function, and there's a curve underneath. Usually a curve is called C, which is the path. And the way you integrate this, just like this was, you integrate the function dx, which is supposed to represent a tiny change in x, times, so you're taking imaginary infinitely thin slices of this function. Similarly, you're going to take tiny slices, but instead of dx or dy, it's going to be ds, a small change in the arc length of this curve. And so, when you want to take these integrals, basically what you'll do is you will take C, your curve, and you'll parametrize it, x of t and y of t, to bring everything in terms of t, and then your integral over C of f of x, y ds. So now ds, as we know earlier, talking about this, is just derivative of x with respect to t squared plus derivative of y with respect to t squared dt. Then you can substitute this for ds. You can substitute x of t for x and y of t for y into your function. And then this t will have some bounds. We'll go from some a to b as we trace this path, say from here to here. From this point t equals a to this point t equals b. So this will become, you go from a to b, f of x of t, y of t, x prime t squared plus y prime t squared dt. So now everything is in terms of t, and you can solve it like a regular integral. Let's do an example. Let's use a relatively simple function, one that we're kind of familiar with. So our function is x squared plus y squared, which we know looks something like this. And let's say our curve is going to be something like this. So that's part of an ellipse. Maybe draw it over here in the XY plane. It's going to look something like this. We're trying to find the integral over c of f ds. So basically we're just trying to find the area of this region right here. And now we begin with finding a parameterization for C. So this is C. What it is, well, the parametric equations for an ellipse are sort of like a circle except stretched in the x direction. So this is going to be stretched by 2, so it's going to be 2 cosine t, y equals sine t. And so this will go from t equals 0 to pi over 2. So now we can start substituting. So ds is going to be square root of what? Well, derivative of x, derivative of 2 cosine of t is going to be negative 2 sine t squared plus derivative of sine t should be just cosine t squared, cosine squared of t dt. Basically, this is just square root of 4 sine squared t plus cosine squared t. That's ds. And so, well, we know f of x is x squared plus y squared. And so what is this going to be? So f of x, y is actually, well, x is 2 cosine t, so it'll be 4 cosine squared t plus y squared is just sine squared t. Now we can substitute all of this into our integral, 0 to pi over 2. Now you can see these integrals usually can't be solved very easily in closed form because these square roots become very complicated. But let's modify this a little bit just for the sake of example. Let's say we had just a semicircle right here, and this would be a 1. Change that to a 1, we would have just 1 sine squared here, so this would just be sine squared t plus cosine squared t, which would be 1. So square root of 1 is 1, so ds would equal dt in this special case. Then f of x, y would also be just 1 as well. You see, this would be a very simplified version. This is not the same as this. It's if this were a circle instead, would just be 0 to the power 2 of just 1 dt, so it's just pi over 2. And so you can see most of the time it'll probably be something unsolvable, or at least you can't find a very easy way to solve it. But this is how you would do it. Now, another type of integral I want to talk about is also an integral over a path or a line, a curved line, I guess, in the xy plane or even in the xyz space. Is instead of using a function of x and y like that, just a function, a scalar function, is you could use a vector function or a vector field. Let's say f of xy. Now what you can do, one of the things that this type of integral, the vector version of the line integral, is useful for in physics is finding the work. So work, usually we say it's the force dot product with the displacement. If it's a straight line, but if you, let's say you take an object and you move it in a not in a straight line, then what you have to do is say you have a field, a force, and you're moving it like that, and you're applying a force to it in various directions. Let's say this is F, your force. Then you would have to take the F dot product with the displacement at each point, so kind of like a tangent displacement. And this is given by a tiny change in the path, which is called dr, where r is your position vector. So r gives you the position at any point. And dr would be an infinitely small change in the position. So as this dr gets smaller and smaller, I get a better and better approximation of the actual tangent vector to the curve, path C. And that's how you would calculate. You would add up all these small dot products to get the total work done. So let's do another example. Let's do one that we are also familiar with, x, y, which looks something like this. Arrows coming away from the origin. And let's say our particle is going to travel along the curve y equals x squared, this parabolic path from 0 to 1. So once again, the similar process. We're going to take this curve C, I'm going to express it in terms of one variable only. So x is t, we can use x equals t and y equals t squared, t going from 0 to 1 as parametric expression for this curve, from here to there, from 0 to 1, not from 1 to 0. And now we're trying to find dr. Well, r is always going to be the position of where you are, so it's always going to be x, y, or in this case, t and t squared. So dr, you can find this taking the derivative of the vector is just going to be the derivative of each of the components. It's going to be 1 and 2t. And so dr is 1 comma 2t dt. So when we actually calculate it, we're going to integrate, well, x comma y, that's just, I already said, t and t squared, dot product with 1 comma 2t dt. And this goes from, t goes from 0 to 1, like we said. So now we can find the dot product of this. Dot product of t is going to be t times 1, which is t plus 2t cubed dt, which will be, well, the integral of t is t squared over 2 plus, that'll be 2t to the 4th over 4, so t to the 4th over 2, 0 to 1, will just be 1/2 plus 1/2, 0 to 1. And so the work done is 1 in this case by this force along this path. So basically, those are the two types of ways to integrate. One of the ways is with a function and finding sort of the area under this curve, or below the function above this curved path. Or another way to find the work, well, the way to find the work using a vector field, you can integrate the vector field dot dr, dot product with the position vector. And those are basically the ways to take single integrals or path integrals for two different types. One is a scalar function, one is a vector function. And that's basically all about path integrals. And thanks for watching, and I'll see you in the next video.